Hello everyone, my name is Marcos, and today I'm going to talk about our work on using natural language processing techniques to improve manual test case descriptions. Software testing remains a manual activity in several industries, and one of the main reasons for that is because automating tests is something that's very difficult. For example, how do we automatically test if players are having fun or not in a game, or if a level is too easy or too difficult? And also, for example, from a visual testing perspective, how do we automatically verify if an object in a frame looks like exactly to what it is supposed to look like? And as a result of this difficulty to automate tests, test cases are often described only in natural language. And a test case description in natural language might have several fields. For example, a test case name, such as membership purchase in this case, in this example. It might also have an objective, such as verify that the user can purchase a membership. And it might have one or more steps, which are instructions for the tester that the tester must perform to achieve the testing goal, such as in this case, log in with a non-member account, sign up for membership, and verify that the user is a member. So this is a typical example of a test case in natural language. And this is an example of a test case that we use in our work. And very often, those test cases are defined by employees from different departments. You can have, for example, employees from QA and different development teams, all of them working on specifying new test cases simultaneously, and this might lead to problematic test case descriptions, such as unclear or ambiguous test case descriptions, incomplete test cases, or redundant test cases. And all of these problems might make the manual testing even more costly to the company. And if we want to have a more effective and efficient manual testing, we need high quality descriptions. So the descriptions of newly specified test cases need to be reviewed, but having other employees from your team manually going through all these new test cases is very time consuming, and this becomes just impractical in a scenario with a large test suite. So we need an automated approach to improve those test case descriptions. And having such an automated approach brings several benefits. For example, it reduces the time and effort for the whole manual testing. It supports the creation and maintenance of a high quality, more consistent, and more standardized test suite. And this particularly benefits new employees who do not yet have much knowledge about the existing test suite. This approach also reduces the challenges for other tasks such as automation. As prior work already indicated, if in the future you want to use further NLP techniques, for example, to extract knowledge from testing scenarios, having a high quality description of test cases is very important. Or if you want to build autonomous agents, an approach that can help to improve uh, the descriptions of test cases is also important. In this work, we propose an automated framework that provides feedback on how to improve natural language test cases. Our framework has three main components. The first one is the data preparation, in which the test cases are read and preprocessed. The second component is the analysis component, in which we build models to perform different types of analysis to improve test cases. At this moment, we have three main modules to perform three different analyses. The first one is to provide recommendations to improve the terminology of test case descriptions. The second one provides recommendations about possibly missing steps in a new test case. And the third one provides recommendations about uh, existing test cases that might be similar to a new test case. And finally, the last component is the report generation, in which we aggregate the outputs of the analysis modules and present them in a single document to the user. Our framework provides feedback to improve test cases from the Prodigy math game. This is the main product of our industry partner, Prodigy Education. And this game is an online, and web-based educational math game. It is an RPG style game in which players can have battles against other NPCs or against other players, and during the battles the players need to answer math questions, and as the more math questions they get correctly, the easier it is for them to evolve their characters, to learn new spells, and to get in-game items. The dataset that we used for this work is composed of the test cases and steps from the Prodigy math game. We collected more than 3,000 test cases, and each test case has several fields, as I mentioned before, such as the name, objective, and one or more steps. In total, we have more than 15,000 steps, and on average, there are 4.82 steps per test case. I'm gonna go quickly over the three modules for analysis that we have at this moment. The first module is about the terminology improvement. It identifies words in the description of a test case that could be replaced by more likely alternatives. And these likely alternatives are recommended based on their usage in the previous and existing test cases. For example, if a new test case has this step, log into the game with a child account, this module recommends to replace the word child by either member with a confidence of 85, non-member with a confidence of 83, or student with a confidence of 68. And we can see that if we have the word member or non-member, this will be a more clear instruction for the tester, since they will already know if they need to log in with a member or non-member account. For this module, we experimented with statistical and neural language models. For the statistical models, we started by first splitting the descriptions of existing test cases into training and testing sets, and we used the training set to build different types of n-grams, and we computed the conditional probabilities which are used for word prediction. We experimented with the traditional next word prediction task. This is a unidirectional n-gram because it uses only the words on the left to predict the next word on the right. And we also experimented with the fill in the blank task. In this case, we have bidirectional n-grams because they use the left and the right context words to predict the missing word in the middle. For both cases, we built from the unigram up to a 5-gram, and for all of them, we experimented with two smoothing techniques, the backoff and the linear interpolation, and the backoff had a better performance, so we used the backoff smoothing. For the neural language models, we experimented with pre-trained BERT language models. So these are the traditional BERT with the transformer layers with a language modeling head, which is basically a classifier on top. And we experimented with three pre-trained models. The first one is the original BERT. The second one is the distill BERT, which is a smaller version. And the third one is BERT whole word, which is a slightly different version compared to the original, in which the words, you mask the whole word instead of subwords, like in the original BERT. And for all of them, we also used the training set to do a fine-tuning, and we did the fine-tuning using a masked language modeling objective, similarly to what was done in the original BERT. And then we used the updated model weights for the predictions. To evaluate all of those models, we used the Perplexity metric. So this metric, Perplexity, is related to the inverse of a probability of a sentence. So for example, if you have a prediction for a word, you have a probability of that prediction, and using the chain rule, you can get the probability of the whole sentence, and this is inversely related to Perplexity. And the lower the perplexity, the better the model, just because a good language model will have a high probability of a sentence, and since this is inversely related to perplexity, the perplexity of a good model would be low. And to evaluate the models, we used the testing set, and using this set, we computed the perplexity for each sentence in this testing set for all the models, and then we can obtained the distribution of the perplexity. We found that among the n-grams, the bidirectional 5-gram is the best one. We can see here in this plot for the unigram that for both uni and bidirectional, they have the same perplexity. But you can see that for the bigram, the bidirectional has a lower performance, has a lower perplexity, which means a better performance. And as we go high in the order of the n-gram, they have even lower perplexities. So in the end, the bidirectional 5-gram has the lowest perplexity, which means it has the best performance. Among the neural language models, we found that the fine-tuned version of the BERT whole word has the best performance. You can see here in a similar plot that for BERT, the fine-tuned version is a little bit better. For distro-BERT, both versions perform much worse, but for the BERT whole word, they have lower perplexities, which means they have better performances. In the end, the fine-tuned BERT whole word has the best performance here. And please note that we cannot compare this this perplexity for the BERT-based language models with the n-grams just because they were built with different vocabularies. The n-gram models, they have a vocabulary related to our dataset, which is around 2,000 words, while the BERT models have a vocabulary size of around 30,000 words. We also experimented if we could combine the best n-gram with the best BERT-based language model to achieve better results. And we started by looking at the cases where one model fails and the other succeeds, just to understand what causes the failure of one and the success of the other one. And we made two observations. So first, the bidirectional 5-gram performs poorly for unseen context in long sentences, and the fine-tuned BERT performs poorly for domain-specific and short sentences. And we used these two observations to combine the n-gram, the bidirectional 5-gram, with the fine-tuned BERT whole word, and we achieved better results. We basically we look at a few characteristics of the sentence to decide if we should use one or another, the n-gram or the BERT. And based on these characteristics, such as based on the length of the sentence and if there are any unseen context words, we decide which one we're going to use. And to use this module in practice, whenever we have a new test case, we go through each step at a time, and for each step, we mask one word at a time. Then we look at a few conditions, just as I mentioned, based on the characteristics of the sentence, and we decide if we're going to use the n-gram or the BERT model. Once we decide this, we get the top K predictions for the masked word. And then if the original word that we masked is in the top K predictions, it means that the best word is already being used, so we don't make any recommendation. Otherwise, we provide the recommendations obtained with the model. I'm going to go quickly through the second and third modules. So the second module is about the missing test steps in a new test case. And this module recommends missing steps for a new test case based on the steps that frequently appear together across the existing test cases. For example, if you have this new test case, log into the game with a child account, sign up for membership, and verify that the user is a member, this module recommends to add the go to the membership page step. So this would be the revised test case now. And this is suggested just because this step in green appeared together with the other ones in the previous test cases. For this module, we used a frequent item set mining algorithm to identify the missing steps. So we start by feeding all the existing test cases into a named entity recognition model. So we use this model to replace proper names of game assets by generic entity names. So for example, if we have this step, purchase the academy hat, and this one, purchase the B hat, they are considered different when we perform the frequent item set mining. But we want to extract the steps that occur together with them, regardless if they're testing the academy or the B hat. So we apply this NER model and transform this first step into purchase the asset item. So asset item is a generic entity name that we have just to represent, just to say that this is an item of the game, but not necessarily with the name of the item, which is academy hat. We do the same for the other step, and then we can properly compare and get the steps that occur together with these ones across the existing test cases. So after this, we find the sets of steps that occur together, and we build association rules such that if you have test cases A, B, C, you should include test case D just because D occurred together with the other ones in the previous test cases. And finally, for the third model, this model identifies and retrieves existing test cases which are similar to a new test case. For example, if you have a new test case which is about membership purchase, this model retrieves an existing test case about membership flow, which is very similar. Overall, we used different techniques for text embedding, combined with text similarity metrics and clustering techniques for this module. And we integrated our framework to our industry partners' data warehouse and cloud infrastructure through a web application, which can be easily accessed by QA engineers and developers. The application has adjustable parameters to provide some flexibility to the user. For example, the user can adjust the similarity threshold if they want to see more or less suggestions of similar test cases. And also the recommendations can be automatically applied to a new design test case. So we made this integration with their testing platform in a way that if they want to accept a recommendation, they can just click and the recommendation will and the application will automatically modify the description of the new test case and apply the recommendation automatically. So to summarize, I described how problematic test case descriptions can make the manual testing even more costly for companies. I presented the automated framework that we proposed in our work, and I also discussed how we integrated our framework to our industry partners' infrastructure. Thank you.